Okay. Previous talk was about Reedy category and Reedy model structures, but today I wanna complete this talk and give some examples, and after that I'll discuss the topological case, and so we will discuss why in the bar construction we can use not only co-fiber replacements, but also if we take bar functor, this functor will be more topical. Okay, and first of all, I'd like to recall the following Hirschhorn lemma, by Hirschhorn. It's an important lemma. Tells us that if we have D diagrams where D is a Reedy category, D is a Reedy category, and suppose in D diagrams, of course, in some model category M. And suppose we have a diagram. Sorry. Suppose we have a diagram, and in this case, we have a solution of the following lifting problem, where H is defined where H is defined on n-1 filtration of B, and we desire to construct the Lifton on the n filtration, and it is possible if for any, of course, we can form the following diagram. And the solution of the Lifton problem in this diagram is closely related with the one for this diagram. And we will use this fact to prove Kahn's theorem, which I will formulate soon. Okay. Suppose that alpha is an object of D, and degree of alpha is n, and then there is a map which is a solution of this problem if and only if H can be extended over the restriction of B to the and filtration. Okay, and I proved this lemma previous talk, and now I want to recall the definition of the model of Reedy model structure on the category of D diagrams. The category of D diagrams definition. Let D be a Reedy category. Reedy category. Let M be model category, and suppose and we should determine which morphism are Reedy weak equivalence, Reedy cofibrations, Reedy fibrations, and recall that the map between the diagrams is Reedy weak equivalence if for any alpha the map F alpha is a weak equivalence. It's just pointwise weak equivalences. It's just pointwise weak equivalence in M. Second point, the map between the diagrams is a Reedy fibration, cofibration. If for any alpha, the relative relation map this map you can see in the diagram in the Hirschhorn in the Hirschhorn lemma, and this map on the left side, and it is called Reedy relative matching map, and the map between the diagrams is a Reedy cofibration if and only if this relative matching map is a cofibration. Okay, and the last point, that F is a Reedy vibration if for any alpha the relative matching map which you can find on the right side of the appropriate diagram in the Hirschhorn lemma is a vibration. Okay, and I recall the following theorem, the following Kant theorem. Let D be a Reedy category as usual, and then be a category. Then the category of the diagrams in M with the Reedy model structure Oh, sorry. With the Reedy weak equivalences. Oh. Reedy weak equivalences, Reedy cofibrations, Reedy vibrations is really a model category. And the second statement is that if M is left proper, it means that a push out of weak equivalence along cooperation is again a weak equivalence. Then the model category is also left proper model category. Okay, and the same we can state about the right and the left and right simultaneously. Okay, and recall that the main example here is, of course, the model category of the simplicial model category, or the category of diagrams between ordinal category and model category, the category of simplicial objects. Okay, and now we will prove step by step this theorem. In the previous talk, we proved some lemma which tell us that I recall what is the lemma. The lemma states that if for any object beta which has degree is less than alpha, the relative matching map has a left lifting property with respect to some class of morphisms between diagrams, then the induced map of Lattian objects, say this map, has also the left lifting property with respect to S. And the dual statements are for matching objects, for relative matching map, for the relative matching map. Okay, and recall that the proof was based on the induction, of course, induction on the degree of some the induction on colimit over degree is less or equal than some, say, n, and we use also the Hirschhorn lemma, and in this manner we prove this lemma. Okay, and now from this lemma, immediately from this lemma, the following lemma follows immediately. If for any alpha, the relative Lattian map has the left-lifting property versus S, then it implies that for any alpha, the map F alpha has the left-lifting property with respect to every element of S also. Point-wise, of course. It's quite easy. We just decompose the map F alpha. Notice that we have the following diagram. This map is formed by the fact that alpha is just a functor, and also we have a Lattian map from L alpha x to x alpha, and we can form the push out, and by the universal property of the push out, we have the following diagram. And here, these maps are just F alpha, and this one is just a relative, just a Lattian map. Okay, and we have a unique map here, and thus F alpha can be decomposed in the following manner. The composition from X alpha, composition from X alpha to Y alpha through the push out. Okay, but what do we know? We know that this map has a left lifting property at the push out of the map. We know that by the previous lemma, we have the left lifting property here. If then we have the lifting property here. So this arrow has the left lifting property, and the push out we obtain the statement. Okay, and in the And this is from conditions of this lemma. And as we use the fact that the composition of maps which have the left lifting property is a map which has a left lifting property, and we're done. Okay, the next proposition. If some map is a Reedy cofibration, then it implies that F is a pointwise cofibration, and also the map between latching objects is a cofibration for any alpha, of course. And the second, as usual, for the matching objects. This is a Reedy vibration. Then F is a pointwise vibration in M, and the map between matching objects is a vibration in M. Okay, proof. The proof is also easy. We know that F is of course, we will prove the first statement. The second one is similar. F is a Reedy cofibration if and only if we have this relative latching map for any alpha is a cofibration in M. And this one holds if and only if the letter map has the left lifting property with respect to the set of acyclic vibrations. Okay, and it holds if and only if F alpha or any alpha has a left lifting property by the previous lemma with respect to the set of acyclic vibrations in M. Okay, and now we can formulate the following corollary from this proposition. This corollary describes the setting when we have as a we have X as a point and as a initial objects, yeah, and in this case corollary from their proposition. If X is a Reedy cofibrant, then for any alpha, both X alpha and Legend map in alpha of X are cofibrant. Cofibrant objects in M. That is, Reedy cofibrant diagrams are pointwise cofibrant. In particular, Reedy cofibrant diagrams are pointwise cofibrant. And the second point is dual to the one, and the proof is obviously follows from the previous proposition. Okay. Now I want to give the following. I want to give another proposition. If the relative Legend map is a trivial cofibration, then for any alpha, both the map F alpha and the map between Legend objects are trivial cofibrations. The proof is obvious. Okay. And the last proposition. If F belongs to the intersection between cofibrations and weak equivalent, Reedy weak equivalences, then the maps F alpha and the map between Legend objects and also the relative Legend map are trivial fibrations. And also the similar facts holds for in the case of matching objects and relative matching maps. Proof. The statement about F alpha is obvious as from the definition of F. F is a Reedy weak equivalence if and only if F is a pointwise weak equivalence, and also F is a cofibration. Then of course F should be pointwise cofibration. And we see that from the some of lemmas or propositions above, and now notice the following fact: if we will prove that if we will prove that this this map between latching objects is a cofibration, then it's easily to see that the map between the relative latching map will be also cofibration. The proof of this fact looks like the proof for the sum of lemma above, and I recall it. Suppose that this map is a cofibration. So sorry, weak equivalence. This is a weak equivalence. Suppose that this one is a weak equivalence, and then we have the following decomposition. And we know that this one is a weak equivalence, and this one is also weak equivalence. So by two or three property, we can conclude that this map is also weak equivalence. And thus it suffices to prove the statement for the only these maps. And we will do it by the induction. The base of the induction, suppose that degree of alpha equals 0, then this map is an identity map, because we know that these objects are initial objects, and initial objects is unique up to the isomorphism, and this map is just an identity map. Identity. Okay. The induction step. Suppose that the map between latching objects of X and Y is in intersection between cofibrations and Reedy cofibrations and Reedy weak equivalences for any beta such that the degree of beta is less than n. And suppose that alpha be an object of the Reedy category of degree n. Okay, and the discussion above shows that the following relative Lattian map is a trivial cofibration for any beta with of degree less than n. Thus, it implies that the map between alpha S Lattian objects is a trivial by Hirschhorn's lemma. Is a trivial cofibration. Okay. And these lemmas and the propositions can be glued together into the following theorem. The map between the diagrams is in the intersection between cofibrations, Reedy cofibrations, and the Reedy weak equivalences, if and only if for any alpha, the relative Lattian map is a trivial cofibration in M. Okay, and the second, of course, dual statement holds. This is a description of the trivial vibrations. And from this theorem and from the lemmas and propositions above, we can derive the Kahn theorem. Oh, we have a comment. Okay. From these lemmas and propositions above, we can obtain the Kahn theorem, but it's so boring and it's not interesting because we just verify the rest of the set of lemmas and the set of axioms of model categories, but I think we can drop it. Okay, and now we discuss the following example. Example about the push-outs in the model categories. In the previous talks, we dealt with simplicial model categories, and but in the setting, in more general setting, we can do the homotopy limits and colimits, and for example, we can form the push-outs in model category, in any model category. And in this case, we should take as our Reedy category some shape category of diagram. For example, we can consider the following category, which of course has the shape of a push-out diagram. And we will map this diagram in some model category, and after that, so we want to construct homotopy push-out, and the homotopy push-out will be will coincide with the usual push-out if so some non-restrictive conditions are completed. Okay, and if we have the following category with these weights, then I consider some diagram from this category to some model category M. So in this case, the Reedy category the following. Okay, and what is the Lachen and Lachen objects of this diagram? So we know that X is this diagram is in a category of diagrams from D to M, and what is the zeroth Lachen object of X? You can see that this is just initial object, and also calls for the first Lachen object. This is true as because we know that the category, this category is empty because there is no objects of degree is less than 0, and in the second case we have no arrows to the object 1. We see that there are only arrows which map from the object 1 to another object. Okay, and as these categories are empty, we can conclude that this holds. And what is the second Lachen object of X? Just a colimit of this composition where U is a forgetful factor. And this category, of course, have one object, the morphism from 1 to 2, and after applying the forgetful factor, we of course obtain the object 1, and the colimit of this category, which consists of one object, is just the image of this factor on this object. Okay, and suppose that this shape maps to the following diagram. 1 maps to A, 0 maps to B, the object 2 maps to C, and we have the following maps. Okay, yeah, it's just the image of this diagram under this function. Okay, and thus we have that this co-limit is just an object A for x of 0. Okay, so we know that the map between two diagrams is a cofibration in the Reedy category of the diagrams, if and only if the relative Lattian map is a cofibration in M. In our case, we can take X to be an initial object. So in this case, we will obtain that the object Y is a cofibration, is a cofibrant, if and only if the following relative matching map is a cofibration, or we can replace, of course, this term by the just Lattian object of Y in alpha, and it means that we should have that this map should be a cofibration, so it implies that B should be a cofibrant. Also, this map is a cofibration, so A should be a cofibrant, and this one should be a cofibration, so the map from A to C is a cofibration. Okay, and it implies that okay, and it implies that this diagram is a cofibrant if these objects, this diagram is cofibrant if these objects are cofibrant, and also this map is a cofibration. So this diagram is cofibrant in the Reedy in this Reedy model structure, but we can replace, of course, the weights or the following weights, and thus we will obtain the other Reedy model structure. And in this case, this diagram is a cofibrant if A, B, and C is a cofibrant in M, and also G is a cofibration in M. Okay, And of course, we can formulate the following analog of Gambino's theorem, and you can find the proof of this theorem, the following theorem, in the Hirschhorn's book. Theorem the functor, the tensor product functor between the D diagram in simplicial set and D diagram in some model category M is a left Whelan by functor with respect to the Reedy model category. And similarly, the statement is true for the cotensor product. And from this theorem, follow the following corollary. Suppose that we have a morphism between the push-out diagrams. So we consider the diagram in simplicial model category. So of course here we should once again use a simplicial model category setting, but we can prove something without problems using just this theorem, an analog of the Gambino theorem, and the fact that this diagram, which was constructed, is just a cofibrant diagram in Reedy model structure. And these facts produce that here we have a weak equivalence between the push-outs if we have weak equivalences between the push-out diagrams. So it follows obviously because we know that we have the following tensor product with a constant functor from the op to simplicial sets. Hence, by Ken-Brown lemma, we can obtain that the functor, co-limit functor over D is homotopical, and so the induced map is a weak equivalence. Okay, and I want to give the following remark. In the left proper model category, in the left proper model category setting, cofibrant, the cofibrant objects, cofibrant objects condition can be dropped. This is an exercise. It's a quite easy. Okay, and now I want to give some facts about the Eilenberg-Zilber property, but I believe that I believe that somebody would like to talk about this topic. You're welcome. It will be cool. Okay. The question is, what is a characterization of those cosimplicial sets or cosimplicial objects taking values in a set valued functor category? Okay, that are Reedy cofibrant. Oh, and it turns out that this condition is okay. Fix some diagram. Some cosimplicial object in some cosimplicial set, and we say that the element x n cos simplex is non-negative. Oh, sorry. Oh, non-degenerate. If it's not in the image of any monomorphism in delta. Okay, and the nth-Lattian object is a monomorphism when each such expression, what is the expression? Expression x equals the composition of some sigma with z, where sigma is a monomorphism in delta, and z is a non-degenerate simplex. Okay, and the nth Lattian map is a monomorphism. Of course, this condition is needed to be a cofibration. And this Lattian map is a monomorphism when each such expression is unique. And you are welcome to see the details in real. Okay, and if the set of left inverses for monomorphism uniquely characterized that monomorphism, then if we have two variants of the representation of some possibly degenerate simplex X, then it follows that sigma prime and sigma are the same. And it turns out that this is true for nearly all morphisms in delta. The only exceptions are D0 and D1. The exceptions from some rule. Okay, and now I define the Ellenberg-Zilber property. If any degenerate simplex in X is uniquely expressible as the image of non-degenerate simplex under a monomorphism, we say that X has the Ellenberg Zilber property. Okay, and the proposition here tells us that a simplicial object has the Ellenberg-Zilber property if and only if it is unaugmentable that is equalizer between two arrows of two arrows between the zero simplices and one simplices is the initial object. Okay, and now in this setting of the Ellenberg-Zilber property, we have the following lemma, which tell that any bisimplicial set is Reedy cofibrant. Outline of proof, we use the Ellenberg-Zilber lemma for simplicial set, but I believe that somebody tells us what happened now, and okay, and from the following lemma, we will obtain the fact that the Uneda embedding is a cofibrant diagram in appropriate Reedy model structure. what is lemma? Another lemma. If a cosimplicial object X is unaugmentable, then the Lattian map is a monomorphism if X and Y are both unaugmentable, then any pointwise monomorphism from X to Y is also a Reedy monomorphism. That is, its relative Lattian maps are monic. Okay, and sketch of proof. A cosimplicial object in set valued functor category has the Ellenberg-Zilber property if and only if it does pointwise. Okay, and an example. Consider the unit embedding from the order category to the simplicial sets. And of course, this is a functor from the Reedy category delta to simplicial sets, and the equalizer between delta 0 and delta 1, of course, is a empty set. So it follows that this diagram is a cofibrant in Reedy model structure. In the Reedy model structure in this category. Okay, so and we have an interesting question. I don't know the answer. What is the case? What is a bad case? What is the case when the equalizer is not empty. If you know something about this one, you can give an example. Okay, and so from this example and the theorems, we have the following corollary, which was used in the bar construction. We use this fact in bar construction. If M is a simplicial model category, then the realization factor from the category of simplicial objects in M is left Whelan with respect to the Reedy model structure. Okay, let's prove this corollary. We know that the realization factor is just a cotensor product with the Yoneda embedding over the delta category. So from the theorem above, we know that this tensor product functor is left Quillin, and we know also from the combination of an example and the theorem above, lemmas above, that this Yoneda embedding is a cofibrant diagram, and so it followed that this functor is left Whelan. Cofibrant in the Reedy model structure. And by the analog of Gambino's theorem. Okay, and now I want to discuss the topological spaces Satan, homotopy limits of topological spaces in homotopy limits in top Satan. We know that it turns out that the functor, the realization functor from the category of simplicial objects in top preserves weak equivalences between so-called split simplicial spaces. Resolves weak equivalences between so-called split simplicial spaces even they are not really cofibrant, even are not Reedy cofibrant. Why this fact is interesting? This is interesting because in the setting of the bar construction, we know that for computing homotopic cool limits, we should use the bar construction, and for doing that, we know that the bar construction is just a composition with the realization factor and the bar complex factor, and we should use here the cofibrant replacement, but it turns out that we can't. We may not doing so, and it's beautiful. And this fact follows from the fact that this realization factor preserves split simplicial spaces, and this factor gives us the split simplicial spaces. And what is the notion of the simplicial split simplicial spaces? Simplicial space X is split if there exists subspaces, say NN(X) in the set of n simplices of X for all n, such that the following inclusion is an isomorphic. So in the case of bar complex, we can, let me give an example. In the case of the bar complex, if we have a diagram from D to top, the simplicial space is a split simplicial space, and what is the reason? The reason is that we know that this is just a coproduct over elements of nerve. And if we take non-degenerate n simplices in nerve, then we will have an isomorphism between the subspace and the whole space. Okay, and now we want to prove these facts, and for doing so, we observe that when X is split, then we get a push-out diagram. We know that we can construct the realization of some simplicial objects as a just by means of push-outs and from the skeletons. We can form this diagram if we have this diagram in the case of the split space X, then in this case we need we need to define a technical property, so-called a relative T1 inclusion. Definition. An inclusion is a relative C1 inclusion if for any open subset U of A and for any point X in B without A, there is some open subset V, say, of B, such that we have the following. So here is A, sorry, and this is B, and we pick a point, say X, and we should have a open subset of B which doesn't which doesn't contain the X point. Okay, and it can be easily verified that in the this push out is has had a T1 inclusion property. It's an easy fact, and also there is a following lemma which tell that if K is a compact, this lemma is some partial case of a small object argument. If K is compact and we have the following sequence of spaces, and then this is a sequence of a relative T1 inclusions. This is a T1 inclusions. Then any continuous map from K to limit factors through some yk, also like small object argument lemma. The proof is left as an exercise. Okay, and now I can prove the following, the important proposition. If the map between simplicial sets, simplicial objects, is a pointwise weak equivalence of split simplicial spaces, then the map between the realizations is a weak equivalence. Why it's true? It's quite easy, and we know that X is split, so the realization is a co-limit of a sequence of relative T1 inclusions. It follows from the consideration of the following diagram. Okay, and by the lemma above, lemma which looks like small object argument, we have that co-limit of pi k, the realization is isomorphic to pi k of the realization of X for any k. So it suffers to show that the maps are weak equivalence by induction. And it can be done from the following well-known fact in the top setting. We have a push out to construct the nth skeleton of X. We should consider the following push out, and also we can consider another push out for Y. And the map from X to Y, of course, induces the map between diagrams, and we know that these vertical maps are weak equivalences. So the result follows from the fact that weak equivalences have a local property. It means that we use the following lemma. An important lemma. I said that it describes local weak equivalences. Weak equivalences are local. Have local property. Have local property, and the lemma tell that a map, a local property in, of course, the top set. A map F is the category topological spaces. is a weak equivalence if there exists open U and V, open cover of Y, such that we have that the maps are weak equivalence. And applying this lemma to the case of the following diagram, we consider we conclude that the push outs are weakly equivalent. Okay, and thus we can use the bar construction not only for the cofibrin diagrams, but for any diagrams. And if we have a weak equivalence between these arbitrary diagrams, then after applying the bar construction, we will obtain, of course, weak equivalence. Okay, and I think it's all that I want to talk about. If you have any question, you can ask me something.